你说，比如说听声条，拉手，对，跟你讲，对，黄国柱跟你讲。像目前资料可以寄给我好吗？因为你，好，我再去把它。好，谢谢。谢谢。
So this afternoon, I'm supposed to talk to you about driving analytical models called Matlab. The first question, what is symbol? It's using letters, right? Using symbols. It's not actually going to the numeric numbers, but seeing if you can actually understand the problem from basic equations. When we start with Newton's law, F equals ma, and we derive our equations for our system based off of those so that we have a full equation for our answer so that we can actually understand the system dynamics of whatever we're trying to study just by looking at our results and not having to run numerous simulations to understand it. So we'll talk about this mathematical modeling concept. We'll show an example, and then we'll close off. So from this mathematical modeling perspective, we're using mathematical language, those equations, those symbols, F equals ma, to describe what we're studying. We can think of it as a process. There's inputs and there's outputs. And what the inputs have to go through is that mathematical model. Some examples. How much lift is my wing going to give me? I could actually take that wing, put it in a computational fluid dynamics simulation, purely numerical, and get an estimate. But what if I change the dimension of the wing? I have to run another simulation. Mathematical analytical modeling says my lift is equal to something. And now if I were to change one of the parameters, I don't have to do another long simulation. I can actually just understand what's going to happen. I can graph the entire trend. Same thing with electrical load. Something as a function of these parameters. Why develop analytical models? It's just for that forecasting capability. You can look at the equation and understand the trends. You don't need computers or lots of simulations to tell you how the output is impacted by the changes in the input. You can do it directly from the equations. It also means you have a very easy way to optimize the behavior of the output to the desired system. So let's look at an example. We're going to look at a gantry crane. A gantry crane is a crane that takes cargo off a ship and bring it to shore. And when you operate these cranes, you actually want the cargo box not to sway. When you end up at the point where you want to lower it, you don't want it swinging, because if it's swinging, you have to wait. You're wasting time. You want to unload this ship as fast as possible. So if we can actually derive a system of equations for this, we can optimize it. So instead of a large swing on the top, we get almost no swing on the bottom. We just lower the cargo and move on to getting the next one before we're finished, just waiting for that one. We'll want to derive some set of equations. Now this isn't as simple as a system to derive in the short time that we have here. We'll look at a different system, just a pendulum, if you would, and derive those. And then I'll show you this. But to give you more ideas, again, decrease the time. We really want to optimize the time. We're going to do it by minimizing that swing. And we have certain velocity profiles to move that container, that crane. And that's what we're going to play with, the parameters on that profile. But again, we'll start off with that simpler one of just a pendulum. In Matlab, those that are familiar with it, it's all about numbers, right? A equals 5. It's not symbolic. But we have a toolbox, a symbolic math toolbox, that can add that understanding to Matlab. And not only does it add that understanding to Matlab of a symbolic variable, it gets us a very easy-to-use notebook interface for creating those type of symbolic studies. Within this notebook, we can start off by inserting an image of the problem that we're trying to solve. And we want to create the equations of motion with a simple pendulum. We have weight, mass, mg. We have tangential and radial forces. We'll add a little title. We'll calculate the equations of motion. We'll start off simply with that famous Newton law, F equals ma. So I'll define an equation in here. Make that bigger. And F equals ma. The notebook now knows about that. There we go. We have F equals ma stored in a variable in our notebook. So we can continue working with it. We could actually derive the real equation based off the parameters that we had here. The radius, the mass, the angle. If we wanted to say acceleration, in this case, A, is angular acceleration. So we want it to be a function of theta. So we're substituting in A equals R times theta prime prime, double prime. Second derivative. And since theta is only with respect to t, second derivative with respect to t. And th standing for theta. But if we wanted to make it a little more pretty, I can tell our notebook to use symbols like we're used to using. And it's substituted and will display. This is one of the biggest advantages of using the notebook versus using the commands in the Matlab command prompt. The notebook gives you a convenient handwritten type of display, whereas the command interface for doing symbolic would keep you up here. So we can also go back to F. Want to look at that minus put in our equation for F. What is the force actually acting on it as a function, again, of theta? And this is the swing. And overall, we can ask, what's the equation looking like now? UPAD has taken those definitions that we've defined based off our situation, put them into that general equation. It's giving us now a specific mathematical model for our pendulum that we can work with. So if we wanted to actually bring it down to understanding just theta, the change in theta versus other parameters, we can manipulate it just like we would when using pen and paper. Divide the equation by certain factors. Isolate one, move it to the other side. Equation, divide by. And on. Isolates the variable of interest as a function of other variables. Sine theta. This is a differential equation. The change, second derivative, the change of our variable of interest is what we know. We need to solve this to try to get more of an explicit theta as a function of time, no derivatives. So again, we could try to do our pen and paper, or we try to let MuPen and the symbolic math toolbox do it for us. So we'll define an ODE equation. So telling it it's an ordinary differential equation. I'll zoom in on this one after I finish typing. Differential equation, telling it, hey, it's an ordinary differential equation. The equation, in this case, is this equation that we define. Since it's stored in a variable, we can just simply call that variable. You could write the differential equation there if you wanted to. But in order to solve this, in order to solve a differential equation, you need conditions. We're giving it an initial condition. In this case, I'm going to redo this, but we want to give it an initial condition, initial position in the angle. And then we want to give it an initial velocity, angular velocity. That's what the second one should be. I forgot the prime to indicate derivative. So the nice thing is I can actually just come back up here, put the prime back in and let it execute. And you see the initial position, the differential equation, the initial angular velocity, and we have to tell MuPad what are the variables of interest. Solve for theta as a function of time. Everything else is considered parameters, not variables. G is a parameter. R is a parameter. As far as solving this mathematical model, they are viewed as constants, not functions of time. For the solution, engine to solve that equation for us. Did I make a mistake? Can anyone solve that equation as written? The problem is the sine function. How do you solve with a sine function there? There are no known analytical solutions. We have choices. We can actually take this and now put it into our numeric solvers in Matlab. Or we can make an approximation. For small angles, we can say that the sine of theta is approximately equal to theta itself. So we can actually substitute that in. We have a command called subs that will let me operate on that. In our equation, make sine theta equal to theta. Put it in there. Made the substitution for us. We can work with this now. Who here thinks an analytical solution for this equation exists? I do. So we can now ask if we build up our symbolic ODE equation again. So in this case, it's a small angle. And we give it our initial conditions. I'll remember to put the prime in there this time. And again, solve. Voila. We have a solution. We have two solutions. Which one were you expecting? Number one or number two? Probably something even easier, is my guess, because you probably know that R and G should be positive values. You've already dealt with the fact that gravity is down. We know that R is a radius. It's going to be a positive number. It's not going to be 0. G is not going to be 0. You've already made assumptions. The computer can't make these assumptions for you. It can only do what you tell it to do. So you told it to solve, and it will consider all of the cases until you tell it to make assumptions. So if we go back up, we'll do that, just that. We're telling it those assumptions we inherently understood from the beginning. And now the computer, the mathematical modeling, symbolic operations are giving us something that looks like we would derive ourselves. So this was a simple problem. Hopefully you can imagine using these same techniques, the same tool for more complex problems that aren't as easy to do on pen and paper. You can even put in the values. And ask for a plot. Start to understand the solution. How is this angle changing as a function of time? We have the equation. We have a solution. We have a geometric, mathematical model, not geometric, arithmetic model for that. that we can easily plot, solve, optimize, and understand. But what about our gantry crane now? What can we do for that? Well, I'm going to first remind you that this notebook, while it's doing the math for us, you saw I embedded a picture in there. I embedded comments. You can put more in here and have a fully commented notebook that explains your derivation, that can explain your problem. There's your documentation. There's your report on your work. It's right there, and it's active and interactive. People can change things and explore. The calculations will run. But from this, again, we want to actually start to work again with our model. So we want to open up a notebook that I already prepared that works with that gantry cane. So instead of just opening new pad now, I'm going to save something in the Matlab workspace. Here's a model, a workbook, dealing with this gantry crane. In this case, we do have a pendulum, just like we had before. The container's down here. The base of the pendulum moves. Adds a lot more complexity to the problem. Notes explaining the problem. Notes on explaining how we're going to actually derive a solution for us. What I'm going to actually do up here, I'm going to ask the notebook to carry out all the calculations in there. Refresh them since I just opened this up. Again, symbol. We're defining a symbol. Finding our normal vectors. Working on our solution. Creating the Lagrangian, just a method for solving these types of problems, and eventually end up with the equation of motion derived for theta, double dot, just like we had before. The swing as a function of time. So this is double dot. And again, we look at it and we say, there's functions in here, sines, cosines, that are going to prevent us from coming up with an analytical solution to our symbolic ordinary differential equation. But yet the toolbox hasn't failed us. This notepad hasn't failed us in terms of deriving a mathematical model. It still helped us. It got us to this point. It did and carried all these calculations for us symbolically. And now we just have to take our results here and start to use numeric solutions to actually derive out the solution for theta as a function of time, because we cannot analytically solve it here anymore. And this acceleration function, too, is another complication. That's the actual function of the acceleration of that cart, that profile. That's determined by the operator of the crane. This profile is what we'll have control over when we want to minimize the swing. The rest are there. So one of the biggest benefits of the Matlab symbolic math toolbox isn't the fact that you can just do this. There's other tools that can do this. It's how easy it is to take results from this and get it back into Matlab to continue working with all the other work that you're already doing in Matlab. So we can come back into Matlab. And now extract I'll call it swing, get bar. So get variable from that notebook I opened. That's why I actually saved that. The point of this command, nb equals mupeg entry train, is now I have a link through this variable nb from my Matlab desktop to the mupeg notebook. If I have that link, I can ask Matlab to get variables from it, such as the one I was pointing out, the output. Would actually reach into that notebook, extract out that variable, and bring it in as a symbolic variable. At this point, it just brought in that, so I'm wondering if I made a mistake. Again, I'll actually have it execute all. One thing is, when you're doing this, you have to make sure the results are actually live and in memory, not just stored in the file. So that's what I'm just doing by having it reevaluate this notebook, is to refresh all the symbolic results into memory. That allows me now to ask for that variable, and it brings in the equation. Matlab knows it's symbolic, that it's not just letters, but there's meaning behind those letters. So it's in Matlab now, still as a symbolic equation, still not as a form we can use for our numerics. But that's easy enough to fix. Matlab function, give it our symbolic equation, swing, and I would like to store that as a file, as a function I can use, and we will call this ODE equation. Gives me a handle. Tells me, hey, wait a minute, you're asking me to define something that you haven't defined yourself. What is this acceleration thing in the symbolic equation you told me about? Because we haven't defined that yet. But we can ask, edit, ODE equation, and it's done just what we asked. It's created a numeric Matlab function based off our symbolic equation. Two commands. Get variable, get bar, brought the symbolic into Matlab. Matlab function, convert from symbolic to numeric. You now have a link between the symbolic realm, the notebook interface, and the numeric realm of Matlab. And it even warned us, hey, wait a minute, remember, you need to do something here. I don't understand what that is. So you need to tell me what that is. So we're going to use a simple profile to define that. One where it's accelerate the cart, coast, and then decelerate. Bang, coast, bang. So accelerate, coast, decelerate. So we can actually put that now into this function. actually start to look at it. I've already done that, so we don't have to do it here. Acceleration. So it's actually describing quite a bit. Function. So you have that capability. That's the real benefit of wanting to do symbolic math with Matlab. It's the ease of moving between symbolic and numeric. Symbolic itself, though, it still has that benefit of understanding, just by looking at the equation, what's going on, without having to run lots of simulation. We can start to call this now from a Matlab script, so we can start to do the end results. In the end, we still wanted to minimize that swing, right? We derived an equation of motion. We found out that we could not proceed any farther analytically. We have to now go to numerics to try to finish it. So we switched over to Matlab to allow us to do the numerics. We can set up our problem. The length of the arm of the crane, the payload displacement, how far does it actually have to travel from ship to shore, and any other type of situation. Even set up our ODE again, putting those in and looking at results. So just by guessing a profile, acceleration profile, accelerate, coast, and then decelerate, and then this would be at shore. This is the angular displacement, the swing. And you can see we're doing not such a good job, a bad job. It's swinging a lot. We're wasting lots of time for that to decay. We want to go ahead and reduce that. So we're going to take that analytic solution, wrap it in a numeric ordinary differential solution, and wrap all of that in an optimization solver. Vary this profile, in this case vary the length of the two acceleration segments in the magnitude of the acceleration. So we're not letting it vary the entire profile to any random function. We're still saying it's accelerate, coast, decelerate. But vary the heights and the times with constraints, though, because we want it to get to shore in a reasonable amount of time, not for infinite amount of time. To minimize that total swing, we'll just compute an area and let it minimize an area to represent swing amount. So we call f min con. There's our function that was derived from the notebook that's been brought into Matlab, swing calc, and the rest describing the optimization problem. Let's go ahead and solve. Going ahead and running it. It's actually a pretty good-sized problem. So we saw that. We can actually plot the results now. Here's the profile he came up with. Accelerate, coast. Coast is a lot smaller now, isn't it? The amplitude, the magnitude of the acceleration and deceleration has decreased. And so has the swing. We're not swinging as much. When the container gets to shore now, we can lower it. We don't have to wait. But one thing we could check is that we actually solve with one starting condition. This problem may have many local optimization. So within the optimization toolbox, again, we're still linked to that analytic solution. We can actually ask it to start to solve this problem, not with just one initial condition, but with a set of initial conditions so that we truly get the global optimization, not just the local. So that we truly are minimizing the swing, not just finding a solution that is better than before. And that's actually using functionality in the global optimization toolbox. And if you saw my earlier presentation, which is linked to the parallel computing toolbox to help you get your answers faster. We'll go ahead and skip this just so you don't have to run. Well, we can run it. So it actually is going through a bunch of different ones, finding the best. The benefit is still the same. Analytics where you can, so you gain that the biggest sense of understanding, and numerics where you have to actually solve your problem. And when it's done, we'll see that we have even a better possible solution. It will actually give us a set of solutions, and we can pick the best one. It will actually be sorted to by what it considers the best for us. And then after this, we can ask, how can we share our work? Again, we still have that notebook. You saw how the notebook had the ability to add text, add pictures, annotations, to actually fully document our work. So a nice, simple report. The same can be said from our script here that's pulling from that notebook. So we can have two reports now. One describing the analytics symbolic work, one describing the numeric work that we pulled from that, and creating a full solution for us. While we wait, we've gone through this flow of work with our products. We started with equations, though. Typically, when we're talking about Matlab in terms of solving problems, we start with data stored somewhere within a file, database, or hardware we're measuring it directly from. In this case, we're starting with equations, F equals ma. We took that equation, we explored it, we did some mathematical modeling. Right there. We turned that F equals ma into theta double dot equals something. In one case, we were able to actually take that and solve it out to theta of time equals some function that we could just look at and plot and understand. In the more complex case, we couldn't get an analytical solution to the ordinary differential equation. So we turned around and used numerics to continue the mathematical modeling. To share, we can share our notebook, print it out, create a PDF out of it. We have a document. For our script that's running the numeric solution, we can do the same. We can publish it, get a report that, again, we can document our work. Mathematical modeling in Matlab. Diverse modeling techniques, both symbolically and numerically. You can focus on which and use whatever tools best suited for your job. Deriving symbolic expressions with that notebook interface. Understanding to be able to look at that equation with variables that you're used to seeing as you would write down. And then transition to other techniques as you needed to by simply importing and grabbing that variable out of there and bringing it into the numerics. Let's see if our Matlab is close to being done yet. Yep. We can ask for the top 3 solutions. So So before, remember, we had still quite a bit of swing. But when by using that multi-start and exploring the design space more fully, we come up with a solution now. It's almost no swing. And if we want to animate it, watch as it gets there, as it gets to that final point, boom, it's almost perfectly steady. We can just lower it directly. We have no weighting. So we've gone from a problem where we have just swinging away to actually solving it to almost the ideal solution of being able to drop it and minimizing our time. And again, we started off with an analytic solution and really using symbolic math to drive our entire process of solving this. Where we stayed with symbolic, and we found at what point there was limitations to the symbolic that we just, mathematics that we have today just does not have a solution for us. We transition to numerics. But we could do that seamlessly. A couple calls in Matlab to get that solution. If you want to learn more about this, I encourage you, please talk to us today. Some different resources for you that can be found on the MathWorks website. Very good webinar here talking about data-driven fitting. I want to create a mathematical model, but I don't have a form of the equation. I have data, and there's no form, no a sine plus a cosine or y as a function of x that I can express symbolically, but how to actually still create a mathematical model that doesn't use equations. It doesn't have an analytic form. So kind of a different subject. Today we really want to focus on using what we know to create a symbolic expression. Here, there's no capability whatsoever for creating that symbolic expression. You just have data. And how do you create a model from that data that yields outputs that are relevant? That, I guess we have some time, so we can handle a few questions. Back there. Any questions?
So it seems that in the old days we had a text mode, a metal toolbox. So replace it with a graphical new one. So same engine.
So in the past, we had a toolbox that has linked to Maple. This toolbox, the symbolic math toolbox, as of currently, is a new MathWorks product. Its own engine, its own calculations, its own intellectual property. Gives you a lot of the same functionality, but can actually give you some more now. Since it's our own product, you can deploy it. You can deploy symbolic math calculations. We can start to integrate it, as you just saw, by pulling it straight in. We can start to work with parallel computing. It becomes more of a seamless product instead of this bolt-on add-on.
And one more question. Notice we have a EC part. Is the sine function still there?
Excuse me?
A function called EC part. Is still there?
EC
Part?
part?
EC part.
R? Oh, easy plot.
Yeah.
Easy plot, yes, it's still there. The function, so we have functions in MATLAB like plot, surface, that take data and plot it as a line for you. We also had a series called easy, letter E, letter Z, plot, easy surf, that would take equations, symbolic equations, and actually still make a nice line plot for you. They're still there. Any other questions? I thank you all for coming. Please enjoy the rest of the sessions. I think we're catching up a little bit on time, which I'm sure you'll appreciate later in the day.